fabrication finally. You can build repos, you can use design tools. And so this week we're going to do cutting processes. So two-dimensional cutting. The assignment is, as a group, characterize your laser cut, which I'll explain. Then vinyl cut anything. And then on the laser, make a parametric construction kit. And so a fun example of this week's assignment is this student's project, who made a marble track construction kit. And here he's showing it's a binary marble counter assembled from a kit of laser cut parts. That's a nice example of this week's assignment. So first is tools. One kind of cutting tool uses a knife. And so a common version of these in Fab Labs is this machine from Roland. It can cut anything you can cut with a knife. A bigger version is one of these. You can buy 2 Fab Labs for one of these. This is a giant version that makes things like parts for Formula One race cars or luxury leather goods. This is a machine developed by former students called the Other Cutter. Was aimed at a do-it-yourself version of the big Zun machine. And then a very interesting variant is these ultrasonic cutters start with a knife, but they put ultrasonic energy into the knife. And so as a result, you can cut through much thicker wood or plastic by putting ultrasonic energy driving the knife. So I'll talk much more about what you can do on those tools. Then lasers, Epilog, Universal, Trotec, GCC, all make really nice laser cutters. These are ballpark $10,000 to tens of thousands of dollars. Robust, nice machines that are workhorses in the labs. There's a number of vendors emerging, making lower cost, more entry laser cutters like these. And then at the other side, this was started by former students. This is a 3,000 watt laser that can do metal cutting. In my research lab, I have these sorts of few $100,000 lasers that can do micro machining. And in research, we use these kinds of lasers that make ultra fast short pulses of light for research. And I'll talk a bit more about those. 2D cutting includes plasma generation. Don't know what's there. So instead of the laser, these make a plasma. They're more affordable than the lasers. They can do metal cutting, but it's a messier process. It's dangerous, and there's some slag for post-processing. The dream cutting tool is these Wooder jets, and these are hundreds of thousands of dollars. They cut with a supersonic jet of Wooder with a garnet abrasive and can cut through almost anything. But they're expensive. They consume a lot of garnet. You really need a technician supporting it to manage that. And then there are entry-level ones emerging. The Wazer is a startup that are much lower cost, lower power ones that are beginning to show up in Fab Labs. Hot wire cutting can't cut heavy materials. The real killer app for this is architectural trim. You can cut foam and make shapes for things like architectural trim. And then wire EDMs, again, commercially are hundreds of thousands of dollars. These cut with a wire that makes a plasma that can make very high resolution metal shapes. And although he never really quite finished it, this was a version of trying to make an EDM on an EDM one of my students did. It's still a work in progress. These make the things like precision machine parts, the components that go into machines. So within that universe of cutting tools, we're going to focus on the vinyl cutter and the laser cutter. Now, key for this week's assignment is you're going to cut a kit that's parametric and accounts for the laser cutter kerf. So the parametric part is, if you think about the marble construction set, the size of the slot depends on the thickness of the cardboard. And so you need a parameter for the cardboard thickness, and then you need to redesign it around changing the thickness. And I'll show you ways to do it. And then the laser cutter kerf is the laser cutter has a beam size, and a typical size in inches is 10,000ths of an inch. And so when it cuts, there's a gap of that size. And so if you want to make a part of a certain size, if the laser goes on the line, it means you're actually cutting into it about 5,000ths of an inch. And for the kind of joints we're making, that's the tolerance of the joint. And so it means to make the part, you have to offset the laser to account for the size of the beam. And so another part of this week's assignment is offsetting. Beginning laser cutting cuts on the line. More advanced laser cutting accounts for the beam size to actually get the dimensions you want rather than subtracting the beam from it. So to do that for this week, you need a tool that can do parametric design. And we've covered many of them last week. So you can kind of do it in Inkscape. And then this is a link. Inkscape has many extensions. And so there's extensions in Inkscape to do a number of the things I'll be talking about, building on the basic Inkscape. With Rhino, you can do it in Grasshopper. With Blender and Spherechuck. FreeCAD, I'll talk about a specific example for this week. Fusion has all of that nicely built in. SolidWorks and XDesign, Onshape can all do it. And then there is a series of tools emerging that are specifically aimed at 2D cutting and folding. So Peppercura is one of them. VisiCut is one of them. FlatFab is one of them. ExactFlat. These are all not extensions of these general tools, but tools specifically designed around cut assembly. So building on last week, you'll need a parametric tool, and I'll work through an example of that. So then once you have your design, you have to get it to the machine. And so just on the vinyl cutter, you draw on the lines around the vinyl. On the laser cutter, you make the path the laser follows. The machines you're using have printer drivers, and so most of them you can print directly to the machine. That's the most common use. I'm not a great fan of the printer drivers. The reason is, for any one machine, typically there's many, many different screens you have to go through, and there's a lot of settings deep in those screens, and it's different for every machine. And those settings makes assumptions about how you use it. So one of the ways you can get to the machines is mods is something I wrote. This builds on a few other years. And it lets you in a browser build a workflow. And so let me get a test file. So if we take that alien face example, I'll save that. And then in mods, what I'll then do is I'll open that. And then here's where I'm offsetting for the tool diameter. And so I'll calculate the tool path. And so here's a tool path for the laser to cut it. And then here's the settings for the laser. And then this is ready to go to the laser. And so it lets you build workflows that do all the steps to prepare a job for the machine right in the browser. And then it talks not through a print driver, but talks directly to the machine. And so that's what I use. And then for the machines we'll be covering, I'll show you many different versions of how to use this for that. So vinyl cutter. A great example of the vinyl cutter is this was a student project that made a self-flapping crane. So it's an origami crane that can flap its own wings. And to do that, it's using a shape memory alloy that I'll talk about in Output Week. And so one task for the vinyl cutter here is the vinyl cutter scores the material to make the folds for the origami. But it also cuts in copper to make the circuits, and then you take the circuits and lay that on the crane and fold the whole thing together, and that's all made as a vinyl cutter project. So the straightforward use of the vinyl cutter is signs. They make signs on doors, things like that. A really fun thing you can do with it is, although there's special materials, you can use ordinary vinyl. You cut vinyl, and then you can either put it into a t-shirt press, which is a machine I recommend having in the lab. These aren't very expensive, and they heat and squish. They apply pressure and they apply heat. And so this actually melts the vinyl right into the fabric. And so you can use it to put graphics in clothing and fabric. If you don't have the t-shirt press, you can iron it on. But the press is nice to uniformly heat and squish. So you can do thermal transfer. You can do pop-up cards, things that open up when you fold them. You can do origami, where you score it, and you can do kirigami, where in addition to scoring it, you cut it to fold. You can vinyl cut masks for screen printing to make shirts and graphics. You can make flexible and multi-layer circuits. When we get to next week, when you start making electronics, one of the ways I'll cover is you can make electronics on the vinyl cutter, where you cut out the traces, lay it up and encapsulate it, and so you can vinyl cut whole circuits that way. And a handy thing you can do is you can make antennas for radios, for wireless links with the vinyl cutter. This is the standard inventory for Fab Labs. And then there's a number of materials we use for the vinyl cutter. This transfer adhesive is, actually, so there's just vinyl to make signs. One of the materials we use is this, and let me grab that. This looks like vinyl for the vinyl cutter, but it's not. It's actually a cast epoxy film, and it's much tougher than vinyl, and it goes to higher temperatures. And so it's a good material, for example, to make flexible substrates for circuits, or when you want to vinyl cut something that's tougher than ordinary vinyl. Then a very important material we use is this one, and that's this, which is, it's copper with an electrically conducting glue. The glue isn't a great conductor, and so you usually solder if you need a stronger joint, but it's copper. This is much more expensive, $100 or $200 a roll. So you don't use this just for big decorative things, but this is what we use to make electronics with it. There's a wide roll of tape, and this you use to transfer. So when you vinyl cut something, you use this to lift it off and transfer it onto a substrate. And then the last material that's often widely misunderstood is this one, which is a transfer adhesive. And it's a funny sort of thing. It looks like an adhesive tape, but the glue doesn't want to stick to it. So what you do is, if you have something without a backing, you put that on this, you vinyl cut it, and then when you lift it off, it lifts away from the backing, and it leaves the adhesive on whatever you had. And so it lets you put an adhesive backing on something that doesn't have it. So if you print on a piece of paper with a picture, you then put this on it, and then it becomes a sticker or something you can lay up. So those are standard materials we use with the vinyl cutter. They're the knives that cut, the vinyl, the masking tape, the transfer adhesive, copper. Oh, and one other thing you can do is there's special Sandblast stencil, although you can use regular vinyl and it works pretty well. Some of Fab Labs have, and I recommend a Sandblaster. And so these cost a few $100s for a basic one. You can spend thousands, but entry-level ones are a few hundred. And so with this, what you can do is you vinyl cut, you put that on an object, and then you sandblast. And so a killer app for that, for example, is glass. And so if you make a vinyl cut stencil and then you sandblast against that, you can make beautiful patterns in glass or stone or very hard materials that you can't do it. No other of the machines in the lab can do it, but the sandblaster can erode it, and then the vinyl cutter can make a stencil. And even though the vinyl is soft, the softness means instead of the sand bouncing off the glass, it just deforms on the soft material. Now, this vinyl cutter, the settings are the force, how hard you cut, the speed, how fast you cut, the depth of the cut. And one of the issues with it is those don't stay still. Some of the machines we use, the settings never change. The vinyl cutter settings depend on the temperature, on the humidity, on the age of the material, all of that. And so you have to do test cuts first. If on one side you might not go all the way through and it doesn't work, on the other side you go through too far and you shred the material. So each time you use the vinyl cutter, you need to do just some test cuts to characterize it. And the actual cutting by the vinyl cutting is done by a knife, and there's a blade, and you'll barely see it. The blade holder is adjustable, but you're not using this to tighten down on it. You're using this to control the blade depth. And you should barely see the blade. It just needs to stick out just enough to cut through the material. If it sticks out any more than that, you'll shred the material. So that's a very important setting. So then you have your design, you have your material, you put it in the vinyl cutter, then comes weeding. And so weeding is what you call the process of removing the part you don't want and leaving the good part you want behind. If the settings are wrong, if you didn't cut through enough or you cut through so much you shred it, weeding is very frustrating. But if the settings are right, it's a beautiful process. It's very easy to do. But there's a few tricks to do weeding well. And so, in fact, I'll add one link here of a video showing that. So one of the tricks is when you put a material in the vinyl cutter, it only weakly adheres to the backing. And so if you try to weed on the backing right when you take it from the vinyl cutter, everything is trying to come up. So usually it's a much better idea to use the adhesive tape and transfer everything onto the final backing. You might be making decoration on a case or making a circuit, but first transfer everything, the part you do want and the part you don't want, onto its final backing. And then once it's there, weed on the backing, because then there's better adhesion. And so when you lift the part you don't want, the part that's going to stay sticks better. And then the other weeding trick is you don't lift up. If you lift up, you're trying to peel everything. When you weed, you curl. You want to shear, not lift. So you start picking up the part you don't want, and then you start curling it and you shear it off. That way, you're pulling horizontally against the part that's going to stay rather than vertically trying to lift it up. And when you get all of that right, it's actually a beautiful process. You just start pulling and kind of magically everything is left behind. And you don't really have to pay attention to the process. And so it's an art. The people who master this love using the vinyl cutter. It's, I'd say, the least appreciated, most versatile tool in the lab. The people who don't like it get exasperated by the skill. There's real skill in learning how to do that. And again, I'll add some links here, but in electronics, actually, I think I might have it linked on this page. In the Electronics Week. So good. I'll come back. This was a student who fell in love with the vinyl cutter, and he made nice videos. Yeah, so I'll link forward to this, of nice videos showing all the steps of he's first laying out he actually vinyl cuts on a backing to make everything a little stiffer, but he puts out the copper, he lays down the material, he runs it through the vinyl cutter, then he weeds it, then he lays it up. And so I'll link forward to this page from the previous page. He has nice videos showing everything I'm describing. So assignment number 1 is just cut something on the vinyl cutter. The killer app for this week is laptop stickers. The most straightforward thing you can do is just decorate your laptop, but just make anything on the vinyl cutter to get used to just getting a job out on it. And just note my comment that it's one of the most versatile, least appreciated tools in the lab. If anything, the laser cutter is overused and the vinyl cutter is underused. So now we come to the laser cutter. Laser cutters can mark, engrave, and cut. They generally have 2 modes. Raster is they go back and forth, rastering, varying the laser power. So that's like a bitmap image. And then vector is where you draw lines, and if you make the lines light, you just draw lines, and if you make it heavy, you cut. Also, one of the neat things you can do with the laser cutter is you can screen print. So this is made on the laser cutter, and the way it's made is there's the image, and this is halftone, like newsprint. And so the way that's done is you make lots of little holes, and there are a number of different workflows where you take an image and you turn it into the pattern of holes to make that. And once you've done that, there are a number of things you can do with it. So the laser, it can make an image by varying the laser power, but that depends on how the material differentially responds to it. This way, all you need to do is make a hole or no hole, and so it's very forgiving. And then once you've done that, that can be the image. You can use this to screen print, but you can do halftone screen printing. So you can screen print like a shirt that has a continuous tone image. And these are also beautiful if you illuminate them. If light comes through them, you can make beautiful halftone glowing images. So halftoning is a neat process. The focus for this week, though, is on construction kits. So GIC is an example. The name GIC came from years ago when my kids were young. I was showing them a laser cutter, and they thought the laser cutter was cool, but my project was dumb. And so they had the idea of a construction kit. And so it started with my daughter, Grace. So it was Grace's invention kit. And then my son, Eli, got involved. And so it was the Great Invention Kit. and the name has just kind of stayed over time. And so it's GIC. And the idea is 2D parts you can assemble into a 3D structure by snapping them together. And so the laser cutter cuts out these parts in cardboard, and then I'll talk about the joint type. There's a friction fit joint that snaps it. So it's like Lego, but you can make it from cardboard. And so I've got a link here to what an example of doing that in FreeCAD. So in what you're looking at, and if I go back, let me jump ahead. This is the FreeCAD file. And so what I'll show in the video is this is a parametric design where I've got a spreadsheet, and then I lay it out to make the GIC parts. And so a key parameter is the thickness of the cardboard. And again, this is critical because if the cardboard changes by just a few thousandths of an inch, you have to change the design. And so the first thing I'll show is I'll change the cardboard thickness in the spreadsheet, and then you'll see the whole design recalculates. The slots get thinner, and then the part size changes, and the layout changes, and then I'll make it thicker again. And so the parts, everything changes in the parts when I do that. So that's done with a parametric design. So I have the spreadsheet. The spreadsheet numbers are linked to constraints in a sketch. And then when you change those constraints, they propagate through the design to redesign all of the parts. And so that's a parametric sketch. And then also in this file, I'm showing an example of an assembly. And so FreeCAD is very extensible. It's very easy to write both macros and build workbenches for it. And so one of the workbenches, if you go to the workbench add-ons, is an assembly one. And so what I'm showing here is an assembly of the parts. So now what I'll do is if I change the part size, now the parts are bigger. And then what I'll do is I'll redo the assembly, and now they all fit together. And so to show how that works, I'll take apart, I'll clone the part, so I'll make another one. And then instead of just placing it, what I'm going to do is I'm going to give constraints. And so here, a constraint can be an edge or a vertex or a face. Here I'm going to pick two faces and say I want them to touch. So I'm going to take that face of one part, and then I'm going to take the mating face on the other part, and then I'm going to give it a constraint. And you see they just snapped. Now I said those parts want to be touching. And so now if I resize my design, the whole assembly, then I can redo the assembly to put it together. And so here's the file I used in that example. And that shows all of the steps of building a parametric design propagating through. And so any of the parametric tools we covered last week can do something like that. And that's something you'll need to do for this week. This next example is, this is a file for Antimony, a really interesting tool written by a former student. For functional representation design. And in that, what I'm showing is joints. So the simplest joint is just a slot. You slide it together. What's happening here is, if we go back to the image, materials have a coefficient for static friction and then sliding friction. And so there's a threshold. And then the cardboard corrugation is like a little spring. So when you slide this together, you're slightly compressing the cardboard like a spring. And then it's pushing out. And then there's a threshold. And for a force below the threshold, it won't move. And then over that threshold, it'll slide. So you're squeezing it together to make the joint that holds this together. And so the simplest cutout is a slot. But that works terribly. And the reason is the first and important improvement to that is a chamfer. And so a chamfer looks like that. And that's doing two things. One thing it's doing is if you assemble this, but you're not quite lined up straight, the chamfer helps align it. So it helps with misalignment. Without the chamfer, you have to come straight in. With the chamfer, you can be angled a bit. And the other thing it's doing is if the stock is slightly larger than the slot, when you push it into the chamfer, it compresses it just a little bit. The chamfer helps squeeze it to get it into the slot. So if we go back to the video I showed you, when we get up to here, let's see, let's go back to here. So this is showing the parametric design. And so one of the parametric parameters is the cardboard thickness. One is the size of the tile. And then one is the chamfer. And then in this parametric design, it's using that to put the chamfers in. And if you test without a chamfer, it's hard to assemble. With the chamfer, you get a better joint and it's much easier to assemble. So that's a better joint. Now, this next joint is a different strategy. This first joint was a press fit by compressing. If you look at this joint, there's a little bump here and a little cutout there. And so here what we're doing is you compress the bump and it clicks into that hole. So now we're holding the joint not by friction, but by deforming this little bump. The problem with this joint is it rests on how easy it is to compress that little bump, which depends on the material. So the next joint here has a flexure. There's a little beam. And so this is like a belt buckle now. What happens is when you click it together, the beam bends, the bump slides over the top, and then it goes in this little depression. So because of the flexure, you can separate how hard the material is from how hard it is to bend the beam. And so this makes a nice bistable joint that clicks into place. And then to undo the joint, you have to overcome the energy to bend it rather than friction. And so it's a tighter constraint that holds better. A great example of that joint is in one of the early machine making machines. And I don't know if Jonathan Ward is listening in Detroit right now, but Jonathan was one of my students and works with the Detroit Fab Lab. And here are the parts he made to make this machine. And all of that is going on this joint here. It's a slightly fancier one. The pin in the center does an alignment. And then these fingers are beams to control the clicking. And so when you snap all of that together, you get a bistable joint. You can undo it, but it constrains all the degrees of freedom very tightly to make a very rigid connection. And then this last joint is a different strategy still, which is when you slide it together, all these holes line up, and then what you do is you put a pin in the final direction. And so you pin the joint by lining everything up and then putting a post into that. And that leads to things like, this was a paper by a former student, let's see, now at NASA. And this was a paper setting a world record for highest performance ultralight material. Let's see, whoever just coughed, you're not muted. And if you look in here, all these parts fit, and then there's one extra pin coming in here that holds all the directions together. And in this case, it's setting world record material properties by pinning the joint after you line everything up. Okay, so that's a flow from a bad joint to a chamfer, which is the basis you'll probably use for this week, to mechanically bistable joints, to pinned joints as more and more fancy joints that have better and better mechanical properties. And so the joint design is an interesting and subtle thing for this week. Now, to make the joint, if you make a slot and squeeze it together, the tolerance between being too tight and too loose is a few thousandths of an inch. But remember, the laser beam is 10 thousandths of an inch. And so you need to position the beam to within a few thousandths of an inch and control the dimensions for it to be able to make the parts for this week. And when we get to CAM, I'll talk about the offsetting. One of the things I recommend you do this week is make a well, actually, I'll come back to that when I get to the group assignment. Now, other things you can do on the laser cutter, you can make what are called living hinges, where cardboard doesn't curve. But if you make cutout patterns like this, you can make a hinge that lets you continuously bend. So even though you're laser cutting a 2D material, you can turn it into a 3D shape by cutting hinges into that. And then you can put those into more complex structures and make flexures. And I'll show this again in machining week, where you make series of beams that let you continuously bend 2D materials into 3D shapes. And this works for both laser cutting and machining. And you can go beyond that. This is a thesis from a colleague, lab of a colleague. And what it's showing is how to make whole mechanisms this way. Let me find... a lot's going on here. If you cut one beam, it bends. Two of them, by linking them, it maintains a piece horizontally, but it goes up and down. If you then nest two going that way with two going this way, it goes in a horizontal direction. And then if you nest those with ones going this way, it can go in two directions. And so this is actually a motion platform. It moves smoothly in two dimensions, but there's no bearings or tracks or anything moving. The whole thing is done just by making beams that bend. And so you can make rotary and curving and all kinds of motion just by laser cutting beams that bend. So the laser. Laser is amplification of light by stimulated emission. And so what it means is there's a medium that creates gain. You put energy into it, light comes in, and it stimulates emission and gets amplified. So every laser has a gain medium, and that sets the wavelength of the laser light. And then the laser beam goes out through an output coupler, and that the optics of that sets the size of the beam. So the most common lasers you'll be using are CO2 lasers. They're very efficient. You can now buy surprisingly cheaply laser tubes. You can get ones even cheaper than this, but ballpark a few $100s for a few 100-watt laser tubes. Those have come way down in cost. CO2 is 10 microns. It's far in the infrared, which means you can't see it, which means it can be dangerous if it's not contained. And CO2 is good at melting plastic and at burning cardboard or wood. On the other hand, you need a lot of CO2 to cut metal. It's not a good wavelength for metal cutting. This machine has a CO2 laser and a fiber laser. The fiber laser is 1 micron, and that's well absorbed by metal. And so this is showing with a CO2 laser, you can, let's see, that's not what I want. You can, I think there's a video on this page. Yeah, this is what I want. What this is doing, it's sped up, but you raster the fiber laser and it can ablate the copper to do metal, and then the CO2 laser then can cut out the board. Those are much more expensive, tens of thousands of dollars. Then there are solid state lasers that you can double to make short wavelength light. There are excimer lasers that make very short light. And I had mentioned the femtosecond lasers. They're in a crazy regime where if you go back to this laser, this makes pulses of light a few cycles long. And they're so intense in that short duration that the laser pulse is actually stronger than what's holding the material together. And so these actually disassemble materials effectively at an atomic level. And those are used for micro machining to do really tiny features. Now, lasers aren't magic. They don't make material vanish. It has to go somewhere. And so there's a whole stew of things happening when you laser cut. One thing that's happening is you're burning, you're combusting it. One is you can be melting. One is you can be evaporating into a vapor. And one is you can be ablating, where you blast it off. And often some of all of those are happening. So it's important to be aware when you laser cut, the material doesn't disappear. All of these things are happening, but it has to go somewhere. And so that has a number of implications for the laser cutting. So one is the airflow, especially when you laser cut cardboard. It's trying really, really hard to catch on fire. You're putting a lot of energy into a tiny space, and it really wants to ignite. And so key for laser cutting is the airflow. So when you laser cut, almost always there's an air assist where the laser beam's hitting the material, but in addition, you're pushing air from above at the place where you're laser cutting. And then there's an exhaust pulling from below. And you're doing that because you want to take all of these combustion products, all the laser cutting products, and you want to pull them away. So the air assist pushes down, and then the exhaust pulls. And when all that's working properly, you're pulling these products from the laser cutting away, and so the material doesn't ignite. So if you come up to a laser cutter and you see smoke and flame around the cutting place, right away that means the air assist isn't working, and you should stop and figure out what's wrong with it. Then you're producing nasty combustion products. And so if you can, you vent your laser to the outside. But if you vent it to the outside, it's very important you vent it up and away. So if you vent to the outside, but you do it like just facing a sidewalk or a street, you're both being a bad neighbor and you're probably violating local rules because you're putting nasty gases where people can breathe them. So to vent outside, you have to vent where nobody can breathe it. Otherwise, you use a closed cycle filter. And so laser cutter, and so most of the laser vendors sell versions of these closed cycle filters you put next to your laser. And in them, they actually have many stages of filtration. And so you can use those as a closed system in an office. But you need to be aware that the filters have a lifetime, and it's not that long. And if you use the filters beyond the lifetime, you're releasing the gases where you breathe them, and you don't want to do that. Furthermore, after you laser cut, where you've cut is releasing all of these products still. And so if you open the laser cutter right after you're done cutting, it'll release the gases into the room. And so if you come into a laser cutter room and you smell a burning smell or a chemical smell, you should yell at somebody because they open the laser cutter too quickly. When you're done laser cutting, you just wait a minute or so for the exhaust to pull away the combustion products before you open it. I've already mentioned kerf, the beam size. When I talk about cam, we'll talk about ways to offset for that. It's very important to account for it. Now, safety. Laser cutters want to catch on fire. So So this was in my lab at MIT. There were a student was working on the laser cutter, doing a big job. He got bored and went off to do some email. And then he wondered why fire trucks were outside the building. And meanwhile, the whole laser cutter had ignited and threatened to burn down the building. What had happened was the belt on the laser broke. And so the head stopped moving. And so it kept putting all the energy into one place. And he wasn't paying attention, and so it combusted. And so the number one rule on laser cutting is you never leave a laser cutter unsupervised. And so if the material begins to ignite, there's an interlock. And so if you open the lid, the laser will stop right away. If you waited too long and it's really starting to ignite, you then need to put the fire out. And so rather than an extinguisher, it's a really good practice to have a blanket by your laser cutter and you use it to smother the fire. And as soon as you smother it, it's harmless. And so I like to put a line on the floor, tape a bright line on the floor, and have a rule that nobody's allowed to cross that line when they're laser cutting, that you lose laser cutter access if you cross the line. You should yell if you ever see a laser cutter unattended with somebody's back to it. You always need, many fab labs have had terrible accidents from laser cutter fires. It's easy to prevent, but it's a great danger if you ignore it. So the number one rule is to always be watching your laser. Lasers are graded in classes. Class 1 lasers can't do any harm. Class 4 lasers are guaranteed to do harm. The laser cutters you're using, when they're completely enclosed, are class 1. Much more dangerous is to use an open laser. And so I really don't recommend doing that. If you do that with an open laser, you need a completely enclosed workspace to use it safely. As long as everything is working, your laser should be class 1. But you need to be careful. I've tested some cheap lasers and was horrified to see laser light actually getting out of the case and starting to burn the wall of the lab. And so unless you're really sure of your laser, you need to be really cautious about making sure the beam is completely contained. We've talked about venting. Another issue is when you're producing all of the products from the laser, they start to deposit on the optics. And laser optics need to be very high quality for the light to get to where you're cutting. If you laser cut with a dirty lens, it's not dangerous to you, it's dangerous to your lab budget. What'll happen is as the lens starts to get dirty, it'll begin to absorb the laser light and eventually you'll crack the lens and destroy the lens. So part of hygiene with laser cutting is cleaning the optics, making sure they're in good condition. And so all the steps are make sure you have a good workspace, make sure it's partitioned so you stay and use it, make sure there's good air assist and good exhaust going out, make sure your filter's in good condition, and your lenses are clean. When all that works, it's a wonderful tool. When any of those are wrong, this is one of the most dangerous tools in the lab. And the threat isn't appreciated until you have a fire in your lab. So materials. My favorite material is cardboard. And so this is a place we buy it from. These are heavy duty corrugated pads, a ballpark $1 each. To evaluate cardboard, if you take a cardboard, cheap cardboard, if you bend it, it'll just kink. It'll make a flap. Good cardboard, if you bend it, will bow. It'll bend rather than kink. So numerically, cardboard is rated by an edge crush test. But qualitatively, you can learn to get the feel of does the cardboard kink or does it bow? So to make good press fit joints, you need cardboard that bends, that bows rather than kinks. Cardboard that kinks when you make the press fit joint will sort of smush together but not be springy. Heavier duty cardboard will bow. And so most high quality boxes to ship products are heavy duty cardboard. You should get it in the habit of always saving your packing material as something you can use with a laser cutter. And this sort of cardboard is a renewable resource. It's very cheap. You can use it in huge quantity. And so I recommend doing as much as you can with cardboard. And even if you're going to later use other materials, do your development work with cardboard. You can prototype with it. There's a whole, almost, let's see, most every well-known architect at some point seems to have had a phase making cardboard furniture. And so you can make surprisingly high-performance structures just out of cardboard. And so for this week's assignment, I recommend focusing on cardboard, but you need a really good source. You need a nice supply of heavy-duty cardboard that makes good joints. And good cardboard makes really satisfying joints. Bad cardboard, they're flimsy and annoying. And again, save shipping boxes, but in quantity, this is a nice example of a vendor selling these heavy-duty pads that make great laser cutting material. You can laser cut wood. Let's see, wood link. I'll fix that link, but this is a hobby shop that sells nice wood stock. Let's see. I'll find the link to it. The reason I link to it is you can laser cut wood. The thickness depends on your laser power. The thicker you go, you have to do multiple passes and there's more charring and burning. But say an 1/8 inch is fine, a 1/4 inch is beginning to get thick for wood. But wood thickness varies quite a bit. And the link I'll fix here is to wood that comes in sheets for model making where the dimensions are very tightly controlled. Garden variety wood sheets you get can have quite a range in thickness where the tolerances aren't good for a press fit joint, but you can use a pin joint that's less sensitive for the wood thickness. Acrylic, so there's PMMA, acrylic, plexiglass, perspex, lucite are all the same thing. This is a vendor we often buy from. You can buy sheets of all different thicknesses and shapes, and there's lots of things you can do with it. Acrylic glue is an interesting thing. It actually melts the acrylic and it flows together. So an acrylic glue joint is done right is as strong as the underlying material. So it glues with special acrylic glue. One of the things you can do is you can heat and bend it. And so this is just a simple make example. By heating a wire, you can then bend the acrylic and make curved joints that way. It's a very easy thing. And then this is a really neat project of somebody who's now on the faculty at MIT, where what she does, let's see if this is this is the video I want. What she does is put a material into the laser cutter, and here she's cutting, but then what she's going to do is she's going to defocus it, and she's now taking the defocus beam that's bigger and she's rastering it, and she used it to soften the material. And so she just laser cut a hinge. So she used the laser cutter to make a 3D shape by using it to soften and fold it. Let's see. Palm or Delrin or acetal laser cuts fairly easily, and acrylic bends fairly well to make flexural things, but cracks fairly easy. Delrin is more forgiving. It has a bigger elastic range where you can bend it and it won't crack. It'll just deform. Polycarbonate you can't cut unless you have a very powerful laser. You can machine it. Metal you can't cut unless you have a very powerful laser. And further, it's really important to not put metal in your laser. The reason is you don't want to bounce the laser beam back into the lasers. Lasers are generally unhappy having their beam come back into them. So a metal cutting laser, the metal absorbs it and it cuts it. If you put metal in a laser that can't cut it, you're bouncing the beam back into it. That's bad for the tube. PVC doesn't go anywhere near a laser. The reason is PVC releases chlorine, releases dangerous gases. There isn't an easy way to test. So the main rule is you only laser cut materials where you know where it came from. You don't cut random materials. But a qualitative cut test you can do is a flame test, where if you take a little shaving of the material and you burn it, it'll make a little bit of color. And if you see color when you burn the material, that's a clear sign that it's hazardous for the laser cutter. So for this week, I would focus in on wood. Now for laser cutting, there's a number of settings. So one is power, obviously how much power you put in. If you put in too little power, nothing happens. If you put in too much power, you melt the material or you just burn the material. So there's a range where it's happy. There's a, making a note, there's a speed, where if you go too slow, you're putting too much energy in one place. But if you go too fast, you're not leaving enough energy. Then most of the lasers we're using are pulsed. So there's a pulse rate. If you pulse too slowly, you get gaps and you get an uneven cut. But if you pulse too quickly, again, you're putting too much energy in one space and you need to put it out. So there's a multidimensional space of settings for your laser. And broadly, this gets called speeds and feeds. And so in your lab should be settings for your laser, for your materials. And those stay steady over time until laser tubes have a lifetime of a few years. And over a few years, eventually the laser power will droop. But you should have standard settings in your lab. Lasers differ on the coordinate system. You need to know where your job is on it. And again, lasers can both raster and vector cut. And broadly, you use raster cutting for decoration, or with some tuning, you can do some 3D topography with it. You use vector cutting to make shapes, to cut out shapes. So now to come to the assignment. Each week from now on, we're going to have a group assignment and an individual assignment. The group assignment is something you do collectively in your lab to prepare for the week, and then the individual assignment is something you each do. The group assignment is characterize your laser cutter, and what I want you to do for that is look at, for the materials you're going to be using, what's the right speed, feed rate, and pulse rate, and experiment a bit with making that too big or too small. What does it look like if you cut with too much or too little power? And then a second thing to do is actually measure the kerf. So make a piece of a known size, cut out the piece of the known size, and check the size you actually got versus the size you put in to measure the beam kerf. And then another thing to do for this week as the group assignment is, and I strongly recommend this, is make a pattern where you have a big finger and then you start to make it smaller and then make it smaller. And so make a comb where you vary the size and vary it by just like a thousandth of an inch. And if you make that comb and then you see what joints fit in what joints, you'll be able to test what's the right dimension to make a good joint. And you'll be surprised at how small the window is, that you just have to be within a few thousandths of an inch to make the joint. And so for this group assignment, all of that is you don't need to do it individually. Each lab needs to do it each week. So you'll do that together, but just on your pages, just individually note what was done in the group assignment and what you learned from it. And then once you've done that, you're ready to do your assignment. And then for the individual assignment on the laser, I want you to design. And again, you design this. You don't download it. Laser cut and document. It's a parametric construction kit. So the dimensions, and in particular the critical dimension of the cardboard thickness, needs to be built in as a parameter. And I'll come back and I'll show you a few ways to do it. And then I want you to account for the laser cutter kerf. So you offset for the size of the tool, and I'll show you a few ways to do that. And then as part of the design exercise this week, I just want you to think about making it so you can assemble it in multiple ways. So don't make just a box that can be assembled one way. Make a family of parts that can be done multiple ways. And so this example, once again, that I like is he wanted to make marbles, but with this basic set of parts, you can make a track that goes back and forth. Here's his kit. You can make something that holds and releases a ball. You can make flip-flops. And he developed this whole family of marble technology with this kit. And so this is a great example of what I was describing. People have made trees, they've made toys, they've made dinosaurs, but make a system for this week, not just a single thing. So for these two constraints of parametric and offsetting, let me go over a couple ways to do that. So here, I'll save this, and we go into oh no, see, I want to go to CD downloads. So this was the example I was showing you in the video of the construction kit. Let's see, sorry, it looks like there's a problem. I'm doing this in a virtual desktop. I think what's happening, yeah, I'm doing this in the virtual desktop and I don't have this set up properly. So I can't, let me not debug this now. I'll set this up to show it live. But if we go back to the video for the parametric part, just to recap that, if we come up to here, in the FreeCAD example, each of the fields in the spreadsheet I named, and then in the orange here, each of the dimensions is linked to a parameter there. And then each of these positions I calculate in the spreadsheet. And so this is parametric in the cardboard. And one of the ways to do the offsetting is you can do it at this stage, where you could add a parameter to the spreadsheet, which is the laser beam size. And then you could add a dimension offset, and you could offset each of these by the laser beam size to make it both parametric and offsetting. You can also do the offsetting in the CAM. So if we go back to this is a, let's see, let's come back to here for the CAM. One of the ways you can do it is in, we go to mods. I'm going to open a workflow to laser cut. I'll bring in an image. And so let me exaggerate this. I'll make the tool much bigger. And then that's what it looks like if you look down here at that. And then I'll make the tool smaller. And so you see how it's offsetting. And in mods, you can actually look at what's going on. I'm going to do part of a recitation on this. It's actually taking the image, it's doing a calculation that shows the distance to the boundary, and then it uses that to do the offsetting calculation. So if you're interested, the whole workflow is here. But this will read in your part, it'll offset for the distance, and then you can use that to send it to the laser. Fusion knows how to do that. Some of the laser cutter drivers know how to, the more advanced laser cutter drivers know how to do that. But as part of this, I want you to design your part and then include the offsetting for the dimension to it. Okay? So stepping back, that's the range of cutting tools that exist. Recapping CAD for this week. You can, in fact, let me show one other thing. You can go to the printer drivers. If you actually look at mods and you open up these things, in here, oh, see, not that one. In here, this is the thing, for example, for the laser cutter. If you actually look at the code in here, it shows you the commands. And so if you're comfortable with coding, you can actually prepare your own files directly for the laser cutter rather than using the print driver at all. It's not that hard to script to write to it. All the things you can do on the vinyl cutter, underappreciated, and then types of joints, types of lasers, laser caution, and the assignment. So, any questions or comments about any of that?
Yeah, Neil, hi, this is Rajat. Can we discuss curve? I think we have missed that.
Say it again.
Curve.
You're saying, are you saying kerf?
Yeah.
You're asking you're asking me just to review kerf?
Yes.
Yeah. So again, kerf is, if let's say this is the part I'm making, and I'm going to cut it with the laser cutter. The laser cutter, and this is the path the laser cutting is following. So all of this is the material left behind. Kerf, K-E-R-F, is what you call what you call the space left behind. Because the beam isn't infinitely small, it occupies space. And so, and I said a typical kerf is in inches is 0.010 is a typical laser cutter kerf. Now, so the point of kerf is you need to displace the beam by half of that size so that you actually cut that shape. And so you can have the laser cutter draw on your line, in which case you need to change your CAD file. Or depending on the workflow you're using, your workflow can offset and either cut on the inside or the outside of the line. But the point of kerf is you need to displace by that. Now there's one other note I should mention I didn't, which is a laser cutter beam looks like this. I'm exaggerating. So this is the output optics. And then what's called the beam waist is where the focus is tight enough. And that beam waist is a reasonably sharp angle. And so part of using the laser cutting is setting the focal depth. Usually you want that to be as small as possible to get the thinnest line. But sometimes you actually intentionally defocus. Defocusing spreads the power, and that can help with, like, if you want to, if you're having trouble with the material igniting, or I showed the example of where you wanted to soften the material. Occasionally you blur it by defocusing, but usually you focus it to make it as tight as possible. But kerf is the name for that size. And so the point of that discussion I had was either with your CAD tool or your CAM tool, for this week, I want you to account for it. And to understand why I'm stressing that, if you make the comb where you vary sizes by just 1/1000th of an inch, you'll see there's a window of a few thousandths of an inch where it fits beautifully, but on one side you can't fit it together, and on the other side it's floppy, and it's a pretty tight tolerance in between. You'll be surprised how narrow the range is to get a good press fit joint, but that's what a kerf is.
Thanks, Neil.
I just like to simplify that. You might ask, how wide is the cut, is the curve?
Sorry, you're asking or telling. I'm not sure if that's a question or a statement.
I'm making a statement, Neil.
Okay. The statement is the size of the cut left behind.
Correct.
Yeah. And again, beginner laser cutter doesn't account for that when you do anything at all non-trivial with a laser, and that's part of the goal this week, is to account for that. The fact that there's a size, that the beam has a size, and you need to include that in the design process. Other laser questions or comments? Or cutting questions or comments?
Hello, Professor.
Yep.
Hello, can you hear me?
Yeah, I can. Go ahead.
Hi, my name is Charles. I'm from FabLab Winam in Kenya.
Good. Yeah.
Laser cutting around where I come from, most of the materials they usually use is perspex.
Yes.
Because, yeah, perspex.
Go ahead. Yes.
Because they fear that wood will catch fire easily. So most of the time they usually don't recommend it.
Yeah. No, I disagree. So, first of all, I strongly recommend cardboard to start. Heavy duty cardboard cuts beautifully and makes strong things, and there's a little bit of smoke, but no more than that, and it's a renewable resource, and it's very cheap. Perspex is used all the time in laser cutting. The reasons I don't love it, one is when you laser cut it, it releases nasty chemicals, and so it's less good for the environment. It's not easily recycled. It also cracks pretty quickly rather than bending elastically. Wood laser cuts just fine. You need to do the speeds and feeds. Something I didn't mention I should is often depending on the thickness of the wood, you need to do more than one pass. You can't cut all the way through in one go. You do a few passes. But if you experiment with speeds and feeds, you can't cut thick wood. We'll do that with machining. But for things like these press fit kits, there's no problem cutting wood of, thin wood. You just need to characterize your laser. But there's many dangerous things I'll cover through the class. Laser cutting wood is just fine. It just needs to be well characterized. You need to do all the things I said. If you need to supervise the laser, and you need to characterize the laser, but thin wood is no trouble to laser cut. It laser cuts just fine. Here, let me show you a nice example. When I joined you from Chile for the opening of this class, these are some pictures from that. And my student Jake made a full-size kayak, but before that, he made a model kayak. And so, this was a wooden kayak before he did the full-size version that's laser cut. And so, this is a nice example of laser cutting wood.
Neil, here's Andy from Munich. Want to add a new software. I met a professor from HPI, that's a university in Berlin. It's called Kyub, K-Y-U-B, B. Kyub.com. I also can put it in the chat here. It's really beautiful. What is my here? I already had the chat open. It's like cube.com.
Okay.
And you can really easily make these press fit things, and the guy is really working on it continuously to be able to make round shapes. To make like sections and stuff like this. I'm working with this on my Instagram. I posted some
Nice.
stuff.
Is it available?
Yeah, it's in a better version. So if somebody tells me or us, I can hook them up with like a license or something.
Yeah, the one comment on what I see, and in fact, I'm going to add this as a comment, is the bane of laser cutting is everything is flat and has 90-degree angles. But you can make curves by living hinges, by kerfing. There are multiple ways to make curvy things with laser cutters. And so extra credit for this week is make something that doesn't just have flat surfaces. But nice. Let me know how that goes, and if that gets traction, I'll add a link for that.
Yeah, I think it's a problem. Everybody uses this maker case to make boxes and stuff. I think it's really outdated. We need something new, and this is a nice like a visual overview. It's in the cloud. Hopefully, more people will use it in the future.
Okay, good. Yeah, I'll be interested to you experiment with that, and then for next week's review, tell me how you do with it. Yeah. I'm going to add a note here just to say extra credit. And extra credit is sort of a joke. If you do this week's assignment, you've done it. But something to think about is not just making flat things. By making living hinges, and sorry, something I said, but let me explain, is if we go back to here, what's happening in this picture in the upper left is what's called kerfing. And kerfing is where you don't cut all the way through. And you can adjust parameters in a laser to do that. So you can take cardboard and with enough power, you cut all the way through, but without enough power, you cut halfway through. And by doing that in a region, you can make a part that bends on the inside, but on the outside is continuous. And so those are all parts of ways to laser cut in 2D, but make curving surfaces in 3D. That's a even more advanced skill on the laser cutter. Okay, so with that, again, recitation on Monday, hosted by Danielle, on all the kinds of projects you can do if you want to make drones or food or all sorts of things, as a tour of many of these that have grown out of Fab Academy projects. Don't neglect the vinyl cutter, it's fun. Do characterize your laser cutter and respect it. And I look forward to seeing what you accomplish next week. Okay, so recitations again are optional but encouraged. Hopefully see you for that, and then see you in class next week where we'll start making electronics. Bye-bye.
Bye.